Want your compiler to help catch bugs before they happen? There is a small but powerful C++17 attribute that does just that, if you know how to use it. Let's dive into the fallthrough attribute and how it can save your switch logic. Hello everyone and welcome to today's video. In this episode, we are going to dive into a lesser known but very useful feature in modern C++, introduced in C++17, the fallthrough attribute. If you've ever written or read a switch statement in C++, this one is for you. Let's start with a bit of context. In traditional C++, switch statements can sometimes behave in ways that are surprising to new developers. Specifically, if you forget to put a break statement at the end of the case, code falls through to the next case, often unintentionally. Here is a quick example. Now, you might expect this to only print 1 when value is 1, but instead it prints both 1 and 2. This is because there is no break after case 1, so execution falls through to case 2. Now, sometimes fallthrough is intentional. Maybe you want multiple cases to share logic, but other times it's a bug. Prior to C++17, we just had to rely on comments like, "Hey, this is a fallthrough," to tell readers and ourselves that it was on purpose. But here is the problem. The compiler doesn't understand comments. That's where fallthrough comes in. With C++17 and onward, we can now explicitly tell the compiler that a fallthrough is intentional using the fallthrough attribute. This makes our code more expressive and helps the compiler catch bugs. Let's take a look at the same example, but updated with fallthrough. Here, we've used fallthrough after case 1. This tells the compiler, "Hey, I meant to fall through here." So now, if we forget to add fallthrough and don't put a break, the compiler can actually issue a warning, depending on your warning level and compiler flags. Let's think step by step about how this improves things. First, it improves readability. Anyone reading your code knows you didn't forget a break. You actually meant to go into the next case. Second, it improves safety. If you fall through by accident but didn't include the fallthrough attribute, the compiler can help you catch it. Third, it gives you more control over how your switch logic flows, which is especially helpful in large functions or systems with many condition branches. Now, here is something important to remember. The fallthrough attribute must be placed on its own line, and it must appear just before the next case or default label. Also, it only works within a switch statement. If you try to use it anywhere else, like outside a switch or after a return, you will get a compile time error. Here is a real-world use case. This example shows how we can stack behavior logically, while still being clear about what's intentional. Before C++17, all you had was a comment and a hope that people understand what you meant. Now you have the fallthrough attribute, which makes your intent explicit and your code safer. To sum it up, use fallthrough to clearly mark intentional fallthroughs in switch statements. It helps compilers warn you about accidental logic bugs. It improves code clarity and communicates intent to other developers. It's available starting in C++17, so make sure your compiler supports it. That's all for today's video. I hope you now have a solid understanding of what fallthrough attribute does in C++, why it matters, and how to use it effectively. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one. Hey everyone, welcome back to the channel. Today we are diving into something that's both super efficient and kind of underrated in C++. Stud bitset. If you've ever needed to work with binary data, flags, or just want a memory efficient way to store bits, then bitset is your new best friend. Let's start simple. What is a bitset? In C++, stud bitset is a fixed size container that stores bits, ones and zeros. Unlike integers, which also use bits under the hood, bitset gives you direct control over each individual bit. You can set them, reset them, flip them, and even test their values, all with a clean and easy to use interface. Let's think step by step. Say you want to represent 8 bits. You can create a bit set like this. Now you have 8 bits, all initialized to 0. Want to set the third bit? Want to flip all bits? Want to reset everything to 0? You can also access bits just like an array. And here is a really nice feature. You can construct a bit set from a string or an integer. So why would you use bit set instead of something like int? Well, with bitset you get bit level control and built-in methods that make code easier to read and maintain. You can even count how many bits are set, or check if none are set. Another cool trick, you can perform bitwise operations directly. To sum it up, stud bitset is perfect when you want to work with a known, fixed number of bits efficiently, with clean syntax and full control. That's it for this video. I hope you learned something new. If you did, drop a like, maybe subscribe. Catch you on the flippity flip! Hey everyone, welcome back! In today's video we are diving into a super convenient feature introduced in C++20, stud format. If you've ever struggled with formatting strings in C++ using stud cout, printf or string streams, this one is for you. Let's start with the problem. Traditionally, formatting in C++ wasn't exactly elegant. You either had to use stud string stream, which is clunky, or the old printf style functions, which are type unsafe and prone to bugs. Wouldn't it be nice to format strings cleanly and safely like in Python? Well, with C++20 you can with stud format. Here is a simple example. Just like that, hello world gets printed. No need to mess around with streams or worry about types not matching format specifiers. Let's think step by step about what's going on here. Stud format takes a format string and any number of arguments. Inside the format string, you use curly braces as placeholders. Each curly brace is replaced by the corresponding argument in order. It's clean, it's readable, and it's safe at compile time. Now, what if you want to include formatting options? You can easily do it like this. Here, less than 10 left aligns the first value in a field of width 10, and greater than right aligns the second value in a field of width 5. This gives you tight control over output layout, perfect for building tables or logs. And the best part, it works with user-defined types too, as long as you implement a formatter. That gives you complete flexibility. You can even format numbers like this. This prints the number in hexadecimal with the 0x prefix. No manual conversion required. So why should you use stud format? Well, it's modern, safe, type-checked at compile time, and incredibly clean. It's part of the format header, and it's here to replace many of the old, clunky formatting techniques we've dealt with for decades. To wrap up, if you are using C++20 or later, stud format is an absolute game changer. It makes your code cleaner, safer, and more professional. That's it for today's video. Don't forget to like and subscribe. Catch you on the flippity flip! Hello everyone and welcome to today's video, where we break down one of the exciting new features introduced in C++20, the spaceship operator, represented by this symbol. In this video I'll explain what this operator does, how it simplifies comparisons, and why it can be a game changer in writing cleaner and more maintainable code. Let's start with a bit of background. The spaceship operator is also known as the three-way comparison operator. Traditional C++ comparisons using operators like less than, greater than, and so on often lead to verbose code when implementing sorting algorithms, or even basic object comparisons. With the spaceship operator, the language provides a unified way to compare values. It's designed to return a value that clearly indicates whether the left-hand side is less than, equal to, or greater than the right-hand side. When you write an expression like this, the operator evaluates the relationship between the two operands and returns an ordering result. This result is typically one of several types of ordering categories, provided by the standard library, such as stud strong ordering, stud weak ordering, or stud partial ordering. Each category informs the user of the precise nature of the comparison. For instance, if the operands are completely ordered with no ambiguity, stud strong ordering is returned. Let's think step by step about how this works. Imagine you have two integers. In this case, since 5 is less than 10, the spaceship operator returns a value that indicates the relationship. This single operator replaces several lines of code that you might have otherwise written, like checking for equality first and then comparing which is greater or less. This reduction in verbosity not only makes your code cleaner, but also minimizes the potential for errors. Moreover, the spaceship operator enables the compiler to automatically generate default comparison operators for your user-defined types. By simply marking your class with the appropriate defaulting, you allow the compiler to deduce the proper behavior based on your members. Consider a simple class example. In this example, the operator first compares the x coordinates. If those are equal, then it moves on to comparing the y coordinates. This built-in logic streamlines the process of ordering objects. It's intuitive and saves valuable development time. That's it for today's video. I hope you now have a clearer understanding of how the spaceship operator works in C++ and why it's such an important addition to the language. Catch you on the flippity flip! Hey everyone! Today we are going to talk about something that's both simple and powerful in C++, stud system. So what exactly is stud system? In short, it's a function that lets your C++ program run system commands, just like you would in a terminal or command prompt. It's defined in the cstdlib header, and you can use it like this. That string you pass to stud system gets sent to the underlying shell. On Windows, that's usually cmd.exe, and on Unix-like systems, it's typically pin/sh. Let's take a quick example. Suppose you want your program to list all files in the current directory. You could do something like this. When this runs, your program will temporarily pause and run the command. Whatever that command prints to the terminal, you will see in your program's output. So why is stud system useful? Well, it can be quick and a dirty way to hook into tools that already exist on the system, like compiling code, launching other programs, copying files, or even calling Python scripts. It saves time when you don't want to write C++ code to do those things manually. But, and this is a big but, you have to be careful with stud system. First, there is a performance hit. Spawning a shell and executing commands can be slow compared to native C++ solutions. Second, it can be dangerous. If you are passing user input directly into stud system, you can open yourself up to command injection vulnerabilities. That's where someone could insert malicious shell commands into your input and potentially take control of the system. Also, because it's OS dependent, code using stud system isn't always portable. A command that works on Linux might fail completely on Windows, and vice versa. So when should you use stud system? Use it when you need something quick, and you are sure it's safe and cross-platform compatibility isn't a priority. But for anything serious or security sensitive, look into native alternatives like C++ file system library, std-thread, or process management libraries like boost.process. That's it for now. Stud system is simple to use, but handle it with care. Thanks for watching, don't forget to like and subscribe. Catch you on the flippity flip! Hey everyone, welcome back. In today's video we are diving into a very cool feature introduced in C++20, stud source location. If you've ever needed to log or track where something happens in your code, like a specific line or function, this feature is going to be super helpful. So what exactly is stud source location? At its core, stud source location is a utility that allows you to get information about the current source code location. The file name, function name, line number, and column number. It's particularly useful for debugging, logging, or any kind of diagnostic information where you need to know where something in the code was executed. Let's start by looking at how to use it. Here we have a simple log message function that logs a message along with where it was called from. The stud source location current is a specific static member function that captures the current location when the function is invoked. Now let's see it in action. When you run this, the output might look something like this. So instead of hard coding file names or line numbers in your logging code, stud source location provides them automatically. But it's not just about logging. It can be extremely helpful for tracing errors, performance diagnostics, and other situations where knowing the context of where a function was called is important. A great example is in custom assertions. Imagine you are writing an assert macro. Now, if an assertion fails, you will know exactly where it happened in your code. Complete with file name, line number, and function name. To recap, stud source location is an awesome new tool in C++20 for tracking where code is executed. It can make debugging and logging much easier and cleaner. And because it's so easy to use, it's something you will likely find yourself reaching for in many situations. Thanks for watching. If you enjoyed this video and found it helpful, don't forget to like, share and subscribe. Catch you on the flippity flip! Hey everyone, and welcome back to the channel. In today's video we are going to talk about a super useful but often overlooked feature in modern C++, the nodiscard attribute. If you have ever written a function that returns a value but sometimes forgot to actually use that value, this feature is for you. Let's break it down step by step. So what does nodiscard actually do? In simple terms, it's an attribute that you can apply to a function or even to a type, which tells the compiler, hey, the return value of this function is important, don't ignore it. If you do ignore it, the compiler will give you a warning. Let's look at a basic example. Now, if you call calculate and just discard the result like this, the compiler will warn you because you probably meant to do something with that value. Why is this helpful? Well, it helps catch bugs early. Maybe you are calling a function that returns an error code or a result you need to process. If you forget to use the return value, your program might silently misbehave. Let's take another example using a class. Now, any function that returns error code will also trigger a warning if the result is ignored. That's perfect for things like error handling, where you really want developers to check what went wrong. This feature was introduced in C++17 and in C++20 it got an upgrade. You can now include a custom message. If someone calls do something and ignores the result, the compiler won't just warn, they will see your message explaining why it matters. Let's think step by step here. You are writing a low-level function. It returns success or failure as a bool. If someone forgets to check that, you might crash later and not know why. By adding nodiscard, you are putting a safeguard in place. To sum up, nodiscard helps make your code safer and your intentions clearer. It tells users, don't ignore this, it's important. Simple, effective, and a great habit to get into. Thanks for watching, and if you found this helpful, be sure to like and subscribe. Catch you on the flippity flip! Hey everyone, welcome back. In today's video we are going to explore one of the most underrated but powerful tools in modern C++, stud string view. If you have ever passed strings around in your programs and worried about unnecessary copies or performance issues, this video is for you. Let's think step by step and see what string view does, and why it's such a game changer. So what is stud string view? It's a non-owning, read-only view of a string. Basically, instead of holding the actual data, it just holds a pointer to a string and its length. This means you can refer to any string-like data, stud strings, string literals, character arrays, without copying the contents. Here is a quick example. Now you can call greet with different types. No need to convert everything to stud string or deal with overloads. String view handles it all. Let's talk performance for a second. Normally, if you pass a stud string by value, it creates a copy. Even passing by const reference means the function expects a stud string. But with string view, you are passing a tiny, lightweight object, like passing a pair of pointers. Fast and efficient. But here is the catch. Since string view doesn't own the data, you have to be careful not to use it after original string goes out of scope. So always make sure the underlying string outlives the string view. Another cool thing, you can do slicing super easily. That's much more convenient than messing with substrings and copies. To sum it all up, string view is a fast, flexible way to work with string data without owning it. It improves performance, reduces copies, and makes APIs more generic. Just remember, it doesn't own the data, so use it wisely. Thanks for watching. If you learned something new today, hit that like button and subscribe for more ++ tips. Catch you on the flippity flip! Hey everyone, welcome back. In today's video we are diving into one of the coolest additions from C++ 20, StudSpan. Now, if you've ever passed around row pointers and array sizes in your code, you know it can be error prone and kind of messy. StudSpan is here to clean that up. It gives you a lightweight, bounce-safe view over a sequence of elements, like an array or a vector, without actually owning the data. Let's break it down step by step. So what exactly is StudSpan? Think of it like a window or a view into an existing array or container. It doesn't copy anything, it just wraps the data and gives you safe, easy access to it. Here is a simple example. Now you can call this function with a vector, an array, or even a C-style array. See how clean that is? No need to pass a pointer and the size separately. And bonus, StudSpan knows its size, so it avoids out-of-bounds access. That's a huge win for safety. Let's think about a typical use case. Before StudSpan, you might have written a function like, then you would have to manually make sure that the pointer isn't null, the size is correct, and you don't read off the end. With StudSpan, all of that gets wrapped into a tidy, expressive package. A span can also refer to just part of a container. It even works with multi-dimensional spans, though that's a bit more advanced. Now keep in mind, StudSpan doesn't own the data, so make sure whatever it's pointing to outlives the span itself. If the data goes out of scope, you are in trouble. To wrap it up, StudSpan is an elegant, zero-overhead way to work with continuous ranges of elements. It makes your function safer, cleaner, and more flexible, all without sacrificing performance. That's it for this one. If you like this breakdown, give it a thumbs up and subscribe for more modern C++ content. Catch you on the flippity flip! Hey everyone, welcome back. In this session we are diving deep into one of the most exciting and modern additions to the C++ 20 standard, StudRanges. If you've been writing C++ for a while, you know how clunky and verbose it can get when you work with algorithms like studsort, studtransform, or studcopy. You are constantly juggling iterators, passing begin and end functions repeatedly. But with C++ 20, the ranges library modernizes this process with a cleaner and more expressive way to deal with sequences. So today, let's understand what ranges are, how they improve the standard library algorithms, how views work, and how you can apply ranges in your real-world projects. First, what are ranges? In traditional C++, when you use STL algorithms, you're passing a pair of iterators to specify a range. That's not too bad for simple use cases. But it can quickly become cumbersome and error-prone as the logic gets more complex, especially when chaining multiple transformations. C++ 20 introduces a new model. Instead of passing two iterators, you just pass the range itself. That means you can now write this. Much cleaner, right? But it goes far beyond just simplifying function signatures. With ranges you can compose transformations, filter data, transform elements, and do it all in a way that's lazy, efficient, and readable. In C++ 20, the ranges library is split mainly into two parts. StudRanges, which includes algorithms like sort, copy, find, etc., adapted to work directly with ranges instead of iterator pairs. StudViews, a set of lazy, composable adapters that let you transform data sequences without creating temporary containers. Let's look at a simple example using StudViews filter and StudViews transform. In this example, we first filter out only the even numbers and then we square them. The result will be 4, 16, 36. What's amazing here is that no intermediate containers are created. The transformation is done lazily as we iterate. This can drastically reduce memory allocations and improve performance in many scenarios. Let's pause and think about why laziness is so important. In traditional C++, if you wanted to filter and transform a vector, you'd often copy the filtered results to another container and then transform that container, or worse, nest loops manually. With views, nothing is evaluated until the final loop runs. That means the actual filtering and transforming logic doesn't happen until you're iterating over the range. So you write what you want, and the range system figures out when and how to execute it efficiently. Let's take a more advanced example. The output of this code will be 40 and 60. Let's walk through it. Drop 2 skips the first 2 elements, so we have elements 3 through 8. Take 4 keeps the next 4, so we only have 3 through 6. Filter keeps only even numbers. Now we only have 4 and 6. And transform multiplies, so we finally have 40 and 60. All of this happens lazily, without unnecessary copies or containers. You might be wondering, what's the practical value of all this? Here are a few major benefits. First, readability. Your code describes what's happening without worrying about how to manage iterators or containers manually. Second, performance. Thanks to lazy evaluation, you don't pay for intermediate steps. You only compute values when you need them. Third, safety. Since ranges operate on containers directly, they eliminate the possibility of iterator mismatches. Fourth, composability. Views are chainable. You can build complex transformations with small, simple pieces, just like building blocks. You can even create your own views if the standard ones don't cover your use case. Here is a tiny custom view example. That's an advanced topic, but it shows that the ranges library is extensible. You can define your own logic and plug it into the pipeline just like any other standard view. You are not limited to views. The standard algorithms in the algorithm header have all been updated with std_ranges equivalents. Here is a comparison. Traditionally, you'd write this, but with ranges you can write this. Std_ranges sort performs additional checks at compile time to ensure you're not doing something unsafe, like accidentally sorting an array of const elements. All views can be chained using the pipe operator. You don't need to nest function calls. That's what makes ranges feel so modern. It brings a touch of functional programming into C++. This pipeline style makes your intentions clear. You can read the code like a sequence of steps, and each step does one thing, clean and understandable. Let's quickly summarize what we've learned today. C++20 ranges allow algorithms to work directly on containers, not just iterators. Views let you build lazy, composable sequences of transformations. Algorithms in the std_ranges namespace offer safer and more expressive ways to process collections. The pipeline syntax brings a modern, readable style to your C++ code. And lazy evaluation can lead to performance improvements and reduce unnecessary memory usage. So if you're writing modern C++, ranges are definitely something you want to integrate into your toolbox. They help you write code that is more expressive, easier to maintain, and often more efficient. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one. Hello everyone and welcome back. In today's video, we are diving into one of the most impactful yet often underappreciated features introduced in C++20, constraint algorithms. If you've ever found yourself writing boilerplate code to make sure your algorithms only work with specific types, or if you've had a hard to diagnose error deep in template code, then constrained algorithms are something you will really appreciate. Today we will explore what they are, why they matter, and how to use them effectively in modern C++. So what exactly are constrained algorithms? Let's start with the basics. Before C++20, most STL algorithms were implemented using function templates. These templates were extremely flexible, but that flexibility came at a cost. For example, if you accidentally try to pass a non-iterable object to std_sort, You might get a compiler error, but not at the point of the call. Instead, you'd get a long, cryptic template error deep inside the STL headers. Not ideal. With C++20, constrained algorithms are now part of the standard. These are algorithms with constraints. That is, they are explicitly restricted to work with certain kinds of input types, using C++20's new concepts feature. Let's think step by step. Before C++20, you could write something like this. That works great, but if you accidentally wrote this, the compiler wouldn't immediately tell you that X isn't an iterator or even a container. Instead, you'd get a long and unhelpful error message about template instantiation. What constrained algorithms do is bring immediate, readable compile time feedback. In C++20, standard algorithms now have constrained versions that use concepts like std sortable, std ranges random access range, and more. Before we get deeper, we need to quickly explain concepts. Concepts are like type traits on steroids. They let you specify requirements for template parameters in a readable and enforceable way. Here is a simple concept. You can now write a template that only accepts incrementable types. If you try to call this with a type that doesn't support the ++ operator, the compiler tells you right away, and the error is actually readable. Concepts like this are exactly what constrained algorithms use behind the scenes. Now, let's look at the constrained algorithms in action. In C++20, algorithms were moved into a new namespace, std ranges. So you now have two flavors of most algorithms. The classic STL version from std, the new constrained range-aware version from std ranges. Here is a classic sort again. And here is the constrained version. Notice the difference? You no longer need to pass iterators explicitly. The constrained algorithm understands that a vector is a random access range, and it uses the right overload internally. If you try to pass in something that's not sortable or doesn't meet the concept requirements, you get a clean and immediate compiler error. But why is this a big deal? Let's explore the advantages. First, better diagnostics. Using std ranges sort with a bad type gives you a clear message that's much better than 50 lines of internal template noise. Second, it's safer and cleaner code. You don't have to manually pass iterators in many cases. Instead of worrying about the iterator, you just pass the container directly. Third, unified interface with ranges. C++20's ranges are more composable and expressive. Constrained algorithms fit perfectly into the ranges world, letting you chain operations more easily. Let's look at some examples and break them down, step by step. The first example is filtering and copying. Suppose we want to copy only even numbers from one vector to another. Using classic STL, we can write it like this. With constrained algorithms and ranges, we can do it like this. Cleaner, right? And if you pass a non-range, the compiler helps you immediately. Let's take a look how constrained algorithms are declared under the hood. Here is a simplified version of how std ranges sort might be declared. This signature does a few things. Ensures that R is a random access range. Requires that its iterator is sortable with the given comparator and projection. Provides defaults for comparator and projection. You get strong guarantees before the algorithm even runs. Constrained algorithms often support an additional argument called a projection. This allows you to sort or search based on member of the object, without writing full comparator lambdas, for example in this code. The third argument, person age, is the projection. It tells the algorithm to compare using the age field. This feature makes code much more expressive and removes boilerplate. And when should you use constrained algorithms? If you are using C++20 or later, and especially if you are working with ranges, you should prefer the constrained versions. If you care about readable, compile time errors, they are a clear win. If you are working with custom types or generic code, constrained algorithms provide safety and clarity. That said, constraint algorithms do have some learning curve. The concepts behind the constraints can be intimidating at first, but they pay off quickly. Let's recap. Constraint algorithms in C++20 live in the stud ranges namespace. They make use of concepts to enforce correct usage at compile time. They simplify syntax by working directly with ranges and containers. They provide clear, readable error messages, making them easier to debug. They integrate naturally with other C++20 features, like projections and views. So while they might seem like just a small tweak at first glance, constraint algorithms represent a big step forward for safety, clarity and expressiveness in modern C++. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one. Let's dive into a mildly useful C++17 feature named optional. So what exactly is std optional? Well, it's a utility that represents a value that may or may not be there. Instead of returning unexpected values or using workarounds, std optional gives us a clean and explicit way to handle missing data. Think of it as a bool flag attached to a variable, indicating whether it is set or not. Now, let's look at some practical applications of std optional. For example, we can use it as a return value type for functions that might fail. Let's see an example. Here we have a function that optionally returns string, in this case the email of the user. If we check for user ID 1, we would get user1 at example.com. Let's test the code. We call the function with user ID 1 and it should correctly return with user1's email. And as you can see, the output is correct. If we check for user ID 2, we get an empty string. But what if we ask for a non-existent user ID, like 19? This is the exact point where optional comes in handy. We can indicate that there is no user with user ID 19 by returning a null optional value. You might ask, couldn't we just return an empty string? Yes, but then we wouldn't know if the user didn't exist or the user just doesn't have an email address, like in the case of user2. So this way, we can differentiate between getting an error while searching for an email and just simply having no email set. For user ID 19, it correctly returns user not found. Another great use case for optional is handling function parameters that may or may not have a value. It lets us pass an empty optional instead of using special default values, like null or null pointer. Here is an example code snippet and the output. Hey everyone, welcome back to the channel. In today's video we are going to talk about something that's simple but incredibly handy in C++. Stud pair. If you have ever needed to return two values from a function, or just wanted to group two related items together, then stud pair is something you should definitely know about. Let's break it down step by step. A stud pair is a class template from the utility header that lets you store exactly two values, possibly of different types. It's like a mini container that holds two elements, first and second. Here is a basic example. In this example we create a pair where the first element is an int and the second is a string. Accessing the values is super easy using .first and .second. You can also use stud make pair helper to create pairs without explicitly writing the types. C++17 made this even nicer by allowing deduction guides, which means you can just write like this, and the compiler figures out the types for you. Now let's think about how this is actually useful. Imagine you have a function that needs to return two values, like a result and a status flag. You can return a stud pair instead of creating a whole new struct. Then when you call it, this is called structured binding, and it was introduced in C++17. It makes working with pairs even cleaner. Another great use case is when working with associative containers like studmap. When you insert a value, the return type is a pair containing an iterator and a boolean indicating whether the insert was successful. So, to sum up, stud pair is a lightweight and powerful way to group two values together. It saves time, reduces boilerplate and works great with modern C++ features like structured bindings. That's it for today's video. If you found this helpful, give it a like and don't forget to subscribe for modern C++ content. Catch you on the flippity flip! Hey everyone, welcome back. In today's video we are going to talk about studany, a powerful and flexible utility introduced in C++ 17 that lets you store any type of value in a type-safe way. Let's think step by step about what this actually means. Normally in C++ when you declare a variable, the type is fixed. An int can only store integers, a stud string holds strings, and so on. But what if you want to write a function or class that can hold anything, without knowing the type ahead of time? That's exactly what studany is for. At its core, studany is a type-safe container for single values of any type. It works a bit like a box. You can put anything in the box, but you need to know what's inside before taking it out. Here is a basic example. In this code we assign an int to a studany variable. To get the value back, we use studanyCast with the correct type. If you cast to the wrong type, it throws a bad anycast exception. Now here is something cool. You can assign any type. For example, so why would you want this? Let's say you are building a plugin system, a scripting interface, or even a UI where values can be of different types. Int, float, string, and so on. Instead of writing a separate logic for each type, you can use studany to store them in a uniform container, like a stud vector containing studany types. But here is the catch. Because it's type erased, you lose compile time type safety. You have to manually cast it back, and if you get the type wrong, it will either throw or fail silently, depending on how you check it. So use it wisely. It's not a tool you want to use everywhere. But when flexibility is more important than strict typing, studany can be a lifesaver. To check the type safely, you can use value.type.name for debugging or use studanyCast to return a pointer that's null if the type doesn't match. Alright, that's a quick intro to studany. It's a clean and powerful way to work with dynamic types while still playing within the bounds of modern C++. Hope this helped. If it did, hit that like button. Catch you on the flippity flip! Hello everyone and welcome back. In today's video we are diving deep into decltype, a powerful but sometimes misunderstood feature in modern C++. Whether you are new to the language or just looking to brush up on your understanding, this one topic you will want to master. So let's get started. Let's begin with a simple question. What is decltype? Decltype is a keyword in C++ that inspects the declared type of an expression without evaluating it and gives you that type at compile time. That means you can use it to deduce the exact type of a variable or an expression, which is incredibly useful when writing generic or template code. Here is a basic example to get us started. So what's happening here? We are declaring a as an int, and then we use decltype a to declare b. Since a is an int, the compiler sees decltype a as int, so b is also an int. This might seem trivial at first, but where decltype really shines is in more complex or generic contexts. Now let's think step by step about why decltype exists in the first place. Before C++ 11, if you had a complicated expression or function return type, you often had to manually write out the type. This could get very messy, especially with templates. With decltype, you can capture the exact type of an expression without repeating yourself or risking type mismatches. Here is a practical example involving functions. Even though add returns an int, we didn't need to know that. We just passed an example call to decltype and it gave us the correct return type. But here is where things get more interesting. Decltype doesn't just give you the type, it gives you the exact type, including constness and reference qualifiers. Let me show you. This precision makes decltype very powerful in templates and metaprogramming. If you are writing a generic function and you want to return the same type as one of its inputs, you can use decltype to capture that type. Here is another real-world use case involving templates. In this template function, we want to return product of A and B. But what's the type of A times B? It could be anything, depending on what types you pass in. Int, double, even user-defined types. Using decltype A times B, we can ensure that the return type matches the result of the expression. Let's take a moment to talk about a common gotcha. Decltype does not evaluate the expression, it just looks at its type. That means you can safely write something like this. One last cool trick. If you want to get the type of a member of a struct, you can do that with decltype too. So to sum things up, decltype is an essential tool in modern C++. It helps you capture exact types at compile time, write more generic and reusable code, avoid manual type declarations and reduce errors, and work effectively with templates, functions and expressions. That's it for today's video. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one. What if I told you there is a function in C++ that never returns, ever? Not because it's broken, but because it's built that way. It can make your code cleaner, faster and even more secure. Let's talk about the underrated noreturn attribute. Hello and welcome back. In today's video, we are going to talk about a lesser known but important feature in modern C++, the noreturn attribute. You might have seen this annotation in some code bases or documentation, and today we are going to break it down step by step what it is, when to use it, and what benefits it brings to your programs. Let's start with the basics. In C++, noreturn is an attribute that you can apply to a function to tell the compiler that this function is not expected to return. In other words, once this function is called, control flow never goes back to the caller. This is useful in scenarios where a function either enters an infinite loop or ends the program by throwing an exception or calling something like studexit or studterminate. It is how you use it. As you can see, this fatal error function is guaranteed to end the program. It prints the message and then calls studexit, which terminates the program. Since the function never returns to its caller, we mark it with noreturn. But why would we want to use this? One reason is that it helps the compiler understand your code better. By explicitly marking a function as noreturn, you are giving the compiler a hint about the control flow. This can help it optimize the code more effectively or issue better diagnostics during compilation. For example, imagine the following scenario. If the compiler knows that fatal error is noreturn, it realizes that any code after that call is unreachable when the condition fails. That means no unnecessary checks or jumps are generated in the assembly, which can slightly improve performance or help detect dead code. Let's look at another common use case, throwing exceptions. Even though exceptions can technically return in a broader sense because the stack unwinds, the important point is that the function does not return to its caller in a regular way. So marking it as noreturn is still appropriate and helps the compiler understand the flow. You might be wondering, what happens if you use noreturn on a function that does return? Well, that's undefined behavior. The standard clearly states that if a noreturn function actually returns, the program's behavior is undefined. So only use it when you are absolutely sure the function never comes back. Now here is something cool. You can use noreturn with functions that are declared but never defined, like placeholders for fatal error stubs or system-specific traps. For example, this code. If this function is called and the linker can't find it, you will get a linker error. This is useful when building frameworks or APIs where you want to clearly signal a fatal path that must be implemented later. Lastly, let's address the formatting. Noreturn is part of C++'s standardized attribute syntax, introduced in C++11. It's more portable and consistent than older compiler-specific macros like declspec noreturn or attribute noreturn. That means your code is more cross-platform friendly and future-proof. So to summarize, noreturn is a useful attribute for making functions that never return. It helps with compiler optimizations, improves code clarity, and allows tools to better analyze control flow. You should use it for functions that terminate the program, throw exceptions without catching them, or loop forever. That's it for today's video. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one. Hey everyone, welcome back. In today's video we are diving into something a little underrated but very useful. Stud placeholders. You've probably seen them used with studbind, but maybe you weren't quite sure what was going on. So let's break it all down step by step. Alright, so what are stud placeholders? In simple terms, they are part of the functional header and are used with studbind to create function wrappers. Kind of like pre-configured versions of functions where some of the arguments are already fixed and others are left to be filled in later. Let's take a simple example. Suppose you have this function. Now let's say you want to create a version of add where the first argument is always 10. That's where studbind and stud placeholders come in. What this line does is create a new function object called add10, where the first parameter to add is fixed to 10, and the second is still open. Stud placeholders 1 means the first argument you pass to the new function. So now you've effectively delayed part of the function call. This is really useful when you need to adapt functions to fit into different APIs, especially ones that expect callbacks or function pointers with a specific signature. Let's think step by step about a real-world use case. Imagine you are working with a GUI library or some kind of event system that expects a function with just one argument, like a callback that takes a button ID. But your logic needs more context. You can use studbind with placeholders to sneak in extra arguments and still satisfy the expected signature. You can chain multiple placeholders too. Now it swaps the two arguments. Kind of cool, right? One thing to note. While studbind and stud placeholders are powerful in modern C++, lambdas are usually the preferred way to do similar things. But for legacy code or quick adoptions, studbind still has its place. That's it for today. Now you know what stud placeholders are and how to use them with studbind to build flexible, partial function calls. If this helped clear things up, give it a like and subscribe for more C++ tips. Catch you on the flippity flip! Hey everyone and welcome back to the channel. Today we are diving into a cool optimization hint introduced in C++20, the likely and unlikely attributes. These attributes allow you to give the compiler valuable hints about which branches of your code are more probable to be taken at runtime. In this video I'll explain what likely does, how it works, when you should use it, and just as importantly, when you shouldn't. Let's break it all down step by step. First things first, likely is an attribute that you can use to indicate that a particular path in your code is the most probable one to be executed. This is especially useful in if and switch statements, where the compiler can use this information to better optimize branch prediction. Here is an example. In this snippet, we are telling the compiler, hey, it's more likely that the user is already logged in, so optimize accordingly. Why does this matter? Modern CPUs are fast, but one thing they don't like is guessing wrong. When there is a conditional branch in your code, the CPU tries to predict which branch will be taken. If it guesses correctly, everything flows smoothly. If not, there is a pipeline stall, which costs performance. By using likely or unlikely, you are giving the compiler a hint so it can organize the generated machine code to match expected runtime behavior. This helps the CPU make better branch predictions. There is also the unlikely attribute, which works exactly the same way, but for code paths that are rarely taken. For example, in this case, you are telling the compiler that it's unlikely this block of code will run, which helps it optimize the normal path better. How does this affect performance? It's important to understand that likely is a hint, not a command. The compiler can choose to ignore it if it thinks it knows better. Also, this doesn't change the logic of your code at all. It only affects performance in specific cases. That said, the gains can be noticeable in hot code paths where branching behavior has a measurable impact. For example, in tight loops that run millions of times, or in systems code where predictability is critical. You can apply likely and unlikely directly to conditional branches. This only applies to statements, not expressions or function declarations. Also, it's worth noting that if you write in the wrong place, the compiler will give you an error, so pay close attention to syntax. You shouldn't just sprinkle likely everywhere, hoping for speed boosts. If you misuse it, you might actually degrade performance instead of improving it. Worse yet, if your guess about what's likely is wrong in production, you are giving the compiler bad advice. So only use it when you are confident about the runtime behavior, or if you've profiled your application and found a clear hot path. Let's say you are building a web server. Most requests are handled without errors, but occasionally something goes wrong. In this example, you are telling the compiler that most of the time the request will be valid. Optimizing that case improves your server's responsiveness under normal conditions. To sum up, likely and unlikely are tools that help you guide the compiler's optimization decisions, but they should be used with care. They are most effective when used in performance-critical code where you understand the branching behavior. If used correctly, these attributes can shave off precious CPU cycles and improve the responsiveness of your application, especially under heavy load. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one. Hey everyone, welcome back to the channel. In today's video we are diving into one of the coolest and most flexible types introduced in C++ 17, std variant. Let's think step by step. Imagine you want to store either an int, a float or a std string in the same variable. In older C++, this usually meant reaching for pointers, unions, or writing some custom class. But now with std variant, it's clean, type safe and way easier to manage. So what is a variant? At its core, std variant is a type safe union. It can hold one of several types, and the compiler keeps track of which type it currently holds. Think of it like a box that can hold either an int, a float or a std string, but only one at a time. Here is a basic example. In this line, data can hold an int, a float or a std string. Let's set a value. Each time, the type inside data changes. But how do we read the value? You can use std_get to access the value. But here is the catch. If you try to get the wrong type, it throws std_bad variant access. So it's best to check what's inside first. Using std holds alternative. Or even better, use std_visit. This will call the lambda with whatever type is currently held. It's clean, modern and works with all types in the variant. Let's consider a use case. Imagine you are building a config system and the setting might be an int, a float or a string. A variant handles that perfectly, without complex inheritance or custom wrappers. To summarize, std variant brings flexibility while staying type safe. It's perfect for modeling data that can be one of many types, and it pairs beautifully with std_visit for clean access. That's it for today's video. If you found this useful, hit like, subscribe, and let me know in the comments what feature you want to see next. Catch you on the flippity flip! Today we are fixing how you handle memory. We are talking about smart pointers. The concept is simple. A smart pointer is a wrapper. It holds a raw pointer to an object. When that wrapper goes out of scope, like when a function ends, it automatically destroys the objects it's holding. You don't have to remember to clean it up. It handles itself. There are 3 types you need to know. First and most importantly, std unique pointer. This should be your default. If you need a pointer, reach for this one first. The rule here is in the name, unique. It owns the memory exclusively. There is no sharing. Because it's the sole owner, you cannot copy it. If you try to copy a unique pointer to another variable, the compiler will stop you. This is a good thing. It prevents two different parts of your code from fighting over who deletes the memory. If you need to move that data somewhere else, you have to explicitly move it. Once you move it, the original pointer becomes empty. It's fast, efficient, and has almost zero overhead compared to a raw pointer. Sometimes unique pointer isn't enough. Sometimes you have complex data structures where multiple objects need to access the same resource at the same time. For that we use shared pointers. Here ownership is shared. The system keeps a score called a reference count of how many pointers are looking at that same piece of memory. Every time you copy the pointer, the score goes up. Every time a pointer goes out of scope, the score goes down. The memory is only deleted when that score hits 0. This comes with a cost. It is slower than a unique pointer because the system has to constantly update that score safely. Do not use this just because you are lazy and don't want to think about ownership. Only use it when you genuinely need shared access. Then finally, we have weak pointers. This solves a specific problem with shared pointers called cyclic dependency. Imagine object A holds a shared pointer to object B, and object B holds a shared pointer back to object A. Neither will ever hit a reference count of 0. They will keep each other alive forever, causing a memory leak. A weak pointer lets you look at the object without increasing the reference count. It's like an observer. It can check if the object still exists, but it doesn't keep the object alive. If the main shared pointers die, the object is deleted, even if a weak pointer is watching it. Here is the summary. Stop using new and delete. Use unique pointer by default. Use shared pointer only when ownership must be shared. Use weak pointer to break loops. Hello everyone and welcome back to the channel. Today we are diving into another modern C++ feature that can make your code cleaner, quieter and more intentional. We are talking about the maybe unused attribute introduced in C++ 17. If you've ever written some code, compiled it and got annoying warnings that a variable or function is declared but never used, then this attribute is for you. In this video we will break down what maybe unused does, why it exists and how you should use it in real-world C++ code. Let's get started. So what exactly is maybe unused? It's an attribute, a kind of annotation that you can attach to variables, parameters, functions and even types. Its main job is simple. Tells the compiler, hey, it's okay if this thing isn't used, it's intentional. When you mark something with maybe unused, the compiler is instructed to suppress any warning it would normally give you about the entity being used. Let's take a simple example. Say you are writing some debug-only code like this. Now, in many compilers with warnings enabled, this will trigger an unused variable warning, because debug value is never actually used. But what if you want to keep it there, maybe for future debugging or conditional compilation? You can fix this like this. Now the compiler knows not to bother you with that warning. Let's think step by step why this matters. In real-world projects, especially large codebases, warnings can clutter your build logs. Even worse, you might miss actual important warnings because they are buried under hundreds of unused variable messages. Using maybe unused helps make your intent clear and keeps your build output clean. Now here is something even cooler. Maybe unused isn't limited to local variables. You can also apply it to function parameters, return values or even entire functions. For example, or maybe you have a utility function that's currently not used, but you want to keep it for future refactoring. The attribute works at multiple levels. It tells other developers and the compiler, I know this isn't used now, but it's intentional. Please don't complain. One important thing to understand is that maybe unused is a standard attribute. The double square brackets are part of C++'s unified attribute syntax that was introduced to make annotations more structured across compilers. Before C++17, compilers had their own non-standard ways to suppress warnings. But now, thanks to maybe unused, you can write portable, readable and warning-free code without relying on compiler-specific hacks. Let's look at a more complex example involving templates. This is incredibly useful when you are building generic code that compiles differently depending on the type. You might have variables that are only relevant in certain branches. Rather than refactoring everything or suppressing warnings globally, you can use maybe unused exactly where needed. So when should you use this attribute? Use it when a variable is conditionally compiled or only used in certain builds, or when a parameter is unused in some contexts but needed to match an interface. Use it when you want to keep code for documentation or future refactoring, and when you are developing in a warning as error environment and want to keep things clean. And that's it for today's video. Maybe unused is one of those small but mighty features in modern C++. It doesn't change how your program runs, but it absolutely improves how your code communicates with the compiler and with other developers. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one.